Okay, we're going to find out how to find the determinant of a matrix. Now, the determinant is only defined for square matrices. So if you talk about finding the determinant, it can only happen for square matrices. Okay, so let's see how that happens and what it gives us, what the determinant tells us. Well, the determinants occur throughout mathematics. For example, a matrix is often used to represent the coefficients of a linear system of equations, and the determinant can be used to solve those equations. Although other methods do exist which solves the equations quicker, but that's one method that you can use to solve a system of equations. The determinant is a scalar value. It means it's a number that can be found by from the elements of a square matrix, and it encodes certain properties of the linear transformation that is described by this matrix. Okay, so the determinant of a matrix A is denoted as follows. Now this is very important because we're going to use some of these notations. So we're going to either write det A in brackets the A, or we can just write det A without brackets, but the most economic way of writing the determinant is using those two bars with the A on the inside. Now folks, don't confuse that with an absolute value. The determinant can be negative. Having it in between two vertical bars does not mean that you have to change the sign of the determinant. Okay, so geometrically it can be viewed as the volume scaling factor of a linear transformation that is described by a particular matrix. Now we're going to deal with transformations of matrix and matrix work later on. Okay, then we'll see, but there we're only sticking to matrices in 2D, so 2 by 2 square matrices. Okay, so the determinant is positive or negative according to whether the linear mapping preserves or reverses the orientation of n space. Now if you're working in 2-dimensional, it's a 2 space, and 3-dimensional, it's 3 space. So if we say the columns or rows of a matrix define the basis of a system, say vectors 3 of a 3-dimensional space, then the determinant will tell you about the volume of the space that is enclosed by those 3 vectors. Let's see what that looks like. First of all, what does the determinant do? It tests for invertibility. It tells us, can we invert a matrix, just like you find the inverse of a function. And when does that tell us? If the determinant of a matrix is 0, then the matrix is singular. If the determinant is not 0, then it is non-singular and therefore invertible. Okay, and how do we use the determinant when we find the inverse? We work with the reciprocal of that determinant. Okay, so if the determinant is not 0, we're going to find out how to find it now. Then the matrix will be invertible. The determinant of a matrix equals the volume of the box in n-dimensional space that are formed by those 3 vectors that forms the matrix. The edges of the box come from the rows of A. In figure 4.1 it shows you there's row 1 entry 1 1, row 2 entry 1 2, entry 1 2 and entry 1 3. That vertex is 3 1, 3 3, 3 2 and 3 3. So each row forms a vertex of this box, obviously coming from the origin. So if you then calculate the columns of A, would then give an entire box with the same volume. Okay, so if you work with the rows or the columns, the volume remains the same. The box would just look differently. Okay, the determinant gives us a formula for each pivot. Theoretically, we could predict when a pivot entry will be 0, requiring a row change. Okay, so from the formula, determinant can be plus or minus the product of the pivots. It follows that regardless of the order of elimination, the product of the pivots remain the same apart from the sign. Sign might be different, the products are the same. So the determinant measures the dependence of the inverse multiplied by B on each element of B. So if one parameter is changed in an experiment, or one observation is corrected, the influence coefficient in the inverse is the ratio of this determinants. Now folks, that's a lot of interesting stuff regarding the determinant, but you don't need to know all of that for the work that we're going to be looking at. It's just interesting to tell you what the determinant is used for, where we find it, how it's represented, and what it gives us. So let's start with finding the determinant of a 2 by 2 square matrix A. Now please note our notation again. A11 is the entry in row 1, column 1. A12 is the entry in row 1, column 2, and so forth. So A21 is the entry in row 2, column 1, row 2, column 2. That's the way we speak about the entries of our matrices. So to find the determinant, all you do is sort of like a cross product. You say A11 multiplied with A22, and you, very important, you subtract it from the product of the other two. So A11 times A12 minus A21 times A12, the second part, and that gives you your determinant of that matrix. Okay, so if we talk about the entries just being A, B, C, and D, it is AD minus BC gives you the determinant of the matrix A, if it's a 2 by 2 square matrix. Okay, so let's find the determinant of each of the following two matrices. Let's start with matrix A. Matrix A, we'll see it's 3 times 4. That diagonal gives me 12. I minus it from the product of that diagonal, which is 2. And that gives me a beautiful 10. 12 minus 2 is 10. It's not 0, so this will be invertible. We will see later on. Okay, let's find the determinant of B. B, the same thing. Minus 3 times 2 is minus 6. I subtract it from the product of the second diagonal. Minus 3 times, or 3 times minus 4 rather, which is minus 12. Gives me minus 6 plus 2, which plus 12, which leaves me with a determinant of 6. Pause the video, quickly find the determinants of C and D, and then we'll come back and see if you're okay with this. Okay. If you worked with the determinant of C, what made it a bit difficult was there's fractions involved. So your laws that govern fractions are important. Minus 3 over 2 times 2 leaves us with minus 3. And the product this way, the 3 in the denominator cancels the 3 in the numerator there and leaves us with minus 5 over 4, which gives us minus 17 over 4. The determinant for D, a very interesting one. Notice that there's zeros. This is a matrix with a number other than 1 on its diagonal. Okay, so let's have a look. If we determine our product, we get 9 minus nothing leaves us with an answer of 9. Okay, so I'm sure you found that very easy. Let us look at a 3 by 3 system. It's a little bit more challenging, so follow carefully what we're going to do. For the 3 by 3 system, there are many ways to calculate the determinant. We will use the most time efficient method. Now you can choose which one of the methods you find more time efficient, more economically time wise. I like the one where we augment the matrix. Now let's see what I mean. I will augment this matrix and use the new matrix that I've formed to find the determinant. Now folks, to augment a matrix is you use the matrix as it is and you add columns onto that matrix. Now for this particular method, I am going to augment this matrix by appending the columns of of two given matrices, usually for the purpose of performing the same elementary row operations in each of the given matrices. Now let's see what it is that we're going to do. There's our matrix. We augment the matrix by repeating column 1 and 2. There we go. You can see column 1 and 2. There's 3 columns in the initial matrix over here. If I just cover the initial matrix over there, there we go. And what do? We use our first 2 columns. Let me get my pen. We used these 2 columns and we augmented the matrix at this point over here. We repeated those 2 columns. Now let's see, what are we going to do with this? Well, there's our augmented matrix. Now follow carefully. We're going to start from the vertex right in the top left corner, and we're going to work diagonally down to the bottom until we reach this particular entry over here. Once we've reached, we go to the top right corner and we work our way backwards until we get to this point over here. Now let's see what I mean. Okay, so we multiply the diagonals as indicated in red and blue, starting at A11. So what am I doing there? I'm going to take A11, I'm going to multiply it with A22 and A33. That's the first number that I'm going to calculate. Okay, then the next number I'm calculating is the product of the diagonal formed by looking at the next entries. Okay, and what do I do with the 2? I add them. The third one, now you can see I have reached my bottom over here. There's nothing more than I can do over there. Okay, so I add that last number. Now I start with A12 and I work the other way around. So A12 times A21 times A33. I add that answer to the next diagonal, A11, A23, A32, the product over there. Then the third one, now you'll see I've reached this point where I need to stop. I multiply, or I add the product of those 3 entries on that diagonal together. Now, yes, now I'm ready to find my determinant of A. I'm going to take the first 3 entries in red, and from those 3 entries in red, once I have added them together, I'm going to subtract the answer to the sum of the 3 entries in blue. Now remember, if you subtract, there's 3 things that need to be added. It will make sense for you to put those 3 things in a bracket. Okay, when we subtract. So let's see. If you have here, you might want to do that. Why do we do that? Because we do not want to lose the sign changes that are following. Okay, so there's a matrix for us to work with. The matrix is 2 minus 1, 1. It's a 3 by 3 square matrix. You can read the entries for yourself. We augment this matrix by repeating the first 2 columns of our initial matrix is repeated here on this side. We've augmented the matrix. We work with the augmented matrix. Starting at the top left corner, we find the product of the entries on that diagonal. So 2 times 5 times 3 is the first thing. We add that to the product of the entries in the next diagonal, and we add that to the product of the entries in the third diagonal. So that covers from top left to bottom right. Now we start at top right and we go bottom left. Okay, blue entries. We add those to the product of the entries on the second diagonal. We add that to the product of the entries in or on the third diagonal. Okay, so it's literally just multiplying like you did in primary school. You're multiplying things together. Okay, so now for the determinant of this matrix. It's the red entries minus, and remember the blue entries is placed in a bracket. Okay, remember that bracket, folks. Don't forget it, because you're going to lose sign changes. So if you want to be safe, first work out the result of the red and the result of the blue, and then subtract the two from each other. Okay, like there, we have that inner bracket. We calculate those products, or the sums, and then we see that the determinant of this matrix A is 67. Okay, later on, important again, if we want to find the inverse of this matrix, that tells us that the matrix is invertible, because the determinant is not 0. Okay, let us try and find this one, and then we'll come back. You put the video on pause, you try and find the determinant of that matrix, unpause and see if you find. Okay, let's have a look. First of all, you augmented the matrix by repeating the first two columns after the third column. Working with that matrix, you multiplied the diagonals with the red, you multiply those three, you add it to the diagonals on the next one, add it to the diagonals on the third, or the entry on the third diagonal, and from that you worked backwards. The blue, you add it to the next diagonal product, you add it to the next product there, and then finally the determinant was the difference between the two. Don't forget the brackets. You do those little sums, you end up with a determinant of 569 for this 3 by 3 matrix. Very quick, almost faultless, as long as you don't forget the negative. Okay, now let's look at an alternative way to find our our determinant of a 3 by 3 square matrix. Okay, let's see how this works. First of all, we're going to choose element A. Okay, then every element that lies in the same column as A or the same row as A, we're going to ignore. So we're going to work with that bottom little part, EFHI, the 2 by 2 little matrix. We can cover those two so that we make sure we do not use them. So what do we do with that? We multiply A with the determinant of this matrix. EI minus, remember, FH or HF, times that number A. Okay? Then we move to the next point B here. Now, if you look at the laser B, we ignore the row and the column. So we're going to ignore A and C and E and H and work with DG and FI. Now let's see what that looks like. There we go. Okay, so the others are all ignored. So we have B multiplied by the determinant of those entries. So DI minus FG. Now please, folks, there was no sign change here. Here we subtract the middle part. We are subtracting. Okay, and for the third one, we're going to cover C, so we cover that row, this row, and we work with a determinant of what remains. And that we are going to add to our already existing set of products that we have. Okay, so it's the first one minus the second plus the third. And once you have calculated that, that's basically the form of the thing that you worked with. You took the A value, the first one, and you ignored the rest and worked with that. You chose the B, you ignored the rest and worked with that. You chose the C there, you ignored the rest and you worked out those determinants, multiplied them with your given numbers in the first row, and that gives you your determinant for the 3 by 3 matrix. Now let's see how this works. We're going to find the determinant of that 3 by 3 matrix. Okay, now that's the form of what we work with. Okay, so it's A multiplied by the determinant of what's left, B multiplied by the determinant, and C. That's the form of what we're going to do. So if we do that, it is 1. Now let's get the highlighter so we can follow what we're doing. The first entry here is 1. So it's 1 times what is left, 15, that product, minus 16 is 15 plus 16. Good. Okay, then we minus what? The next number. So we ignore those two. So we get 10 minus 4. There we go. Then we add. The last entry in the first row is minus 2. Okay? We're adding it. And then we work over here. So minus 8 minus 3 is what we've got left to calculate. And that gives me a beautiful 31 minus the 24. That's 10 minus 4 is 6 times 4 is 24. And this gives us plus 22, which leaves us with a determinant for this matrix of 29. Okay, folks, so not that difficult. Some of you might find this one much easier, as long as you can just train your eye to see what it is that you're looking for. You work with the first rows, there, and there. Now, if there was a minus 4 here, we will have minus 4, which will make it a plus 4 over there. But we have a positive, a negative, and a positive, separating the operations that we are going to undertake. Okay, so alternatively, if we use the old way, we augmented the matrix, we would have had, let's see, 1 times 3 times 5 is 15, 4 times 4 times 1 is 16, we add all of them, 2 times minus 2 is minus 4 times 4 is positive 16, minus the sum of the other way around, so 4 times 2 is 8, times 5 is 40, 4 times 4 is minus 16 times 1 remains minus 16, and then 2 times negative 2 times 3 is minus 6. We find those two sums and we see that our two determinants are indeed the same. So whichever one works for you, you can apply and use from here on going forward. Okay, so what are the properties of the determinant of our matrix? Well, the determinant of an identity matrix is 1. Now you can think of why that is, because you have in the first row entries 1, 0, 0. Okay, so 1 times whatever the determinant is of what is left, and that is 1. And then 0 times whatever gives you the same thing. The determinant linearly is linearly on the first row. We use that first row to find our determinants. The determinant changes sign when two rows are interchanged. Now that might become important later on, so remember these basic properties of the determinant. So if I do a row change, I had CD and AB. Remember, I had AB and CD. So I have CB minus AD. Okay? CB minus AD. Here I have AD minus BC. Okay, so the determinant changes sign when two rows are interchanged. So if we change those two rows around, we change the sign of the determinant. Important. Okay, so two rows. If the two rows in the matrix are equal, the determinant is 0. Excuse me. So if I have determinant or the matrix AB, AB, that will be AB minus AB and gives me 0. What's the property here? Those two rows have identical entries in them as well. Okay, so if two rows of the matrix are equal, the determinant of the matrix is 0. Subtracting a multiple of one row from another leaves the determinant unchanged. Okay, now let's see. If I take a multiple of row 2, say L times C, and I subtract it from row 1, my determinant is going to be the same. It is that multiplied by D minus that multiplied by B minus LD. Okay, and you'll see that it remains AD or AD minus BC, because the LC and the LD take care of one another when you subtract and add them. Okay, so if A has a row of zeros. One row of zeros, it's all it takes to let the determinant be naught. Now look at that. We have a 0 row at the top. We have different entries at the bottom. Naught minus naught remains naught. Okay, now you'll remember what a triangular matrix is. If A is a triangular matrix, then the determinant of A is the product of its diagonal entries. So it has to be triangular, meaning that above the main diagonal we have 0 entries, then it's lower triangular. If it's upper triangular, then below the main diagonal all the entries are 0. So if it's triangular, the determinant of A is the product of the diagonal entries of that matrix. Okay, so let us have a look. Triangular matrix here. There's your main diagonal. Below it is a 0. So AD minus naught times C. Okay, if the naught is on that diagonal entry there, we have here A times D minus B is AD, B times naught. A times D minus naught times C is still AD. So if it's upper or lower triangular, here it's upper triangular, there it's lower triangular, you just take the product of the entries on the main diagonal of our matrix. Okay, so let's see. If a matrix A is singular, then the determinant, so remember singular means the determinant is naught. It will later, we'll see that it's invertible, then the determinant is not equal to 0. So if we have a singular matrix like we have over there, and that is 0, AD minus BC is naught, the matrix is not invertible. Okay, a square matrix that is not singular, in other words, it has an inverse, it means then that the determinant is not naught. Folks, remember that, because that's going to help us when we work with determinants. The determinant of the product AB is the same as the determinant of matrix A plus the determinant of matrix B. Almost reminds you of a log law. The log of AB is the log of A plus the log of B. Okay, so if you want the determinant of two matrices that's been multiplied with one another, all you need is find the determinant of the one, the determinant of the other one, and you add them. Okay, so we'll see that that works exactly the same. Okay, and then the transpose A has the same determinant as the matrix A itself. Now that is almost common sense in a way, because you change your rows and your columns to get to the transpose matrix. Okay, so if we look at this row became that column, we have AD minus BC. Here we have AD minus BC. So the determinant of A is the same as the determinant of the transpose of A. Okay, that takes care of the concept of the determinant of the matrix. If you learned something, please then like the video, share the video, and then subscribe to my channel. Thanks for watching.